Okay. So in this particular session, as a part of our decoder-based RAM verification using SystemVerilog, first we are going to design our design. Okay, that is nothing but decoder-based RAM design. We are going to design. Then we are going to develop our test bench. Okay. So let us see first of all how to come up with the design, and let us go with our verification part. What we are going to do with our verification? Let us try to understand. Right now, let me share my screen. I hope my screen is also visible. Right? Please let me know in the chat box whether my screen is visible. Okay. Yeah. Thanks for letting me know. So we are going to have a particular module. This is our module, which is our decoder based RAM. Now, this decoder based RAM DBR, which is going to have input as clock and another input as reset underscore n, which is an active low reset, and I'm going to have one is known as write enable, and followed by I'm also going to have read enable, and followed by address. This address is of 7-bit width, okay, and followed by w data. This is of 8-bit width, and R data, which is output from this RAM, which is of 8-bit width, and also we are going to have a signal which is known as valid to indicate whatever the data which we want to read is a valid data or not. Now, what is this internal decoder based RAM? This block diagram is going to have is it is going to have four blocks of 32 cross 8. So we are going to have 32 cross 8. That means 32 number of locations, and each location is going to have 8 number of bits. And like this, we are going to have 4 number of blocks 1, 2, 3, and 4. So like this, we have total 32 cross 8, 32 cross 8, and 32 cross 8. So 32 into 4 is nothing but 128. Okay. So total memory locations we are going to have is 128 number of locations. So total locations are 128 locations. And in this 128 locations, instead of having in the same block, we basically divided it into four number of blocks. Each block is of 32 bits, and each location is having 8 bits. Now we are going to have something known as decoder circuit. This particular decoder is going to decode which particular block should be selected according to the address which we are going to provide. This particular decoder is going to decode to which particular address I want to write the data. Okay, so that is the job of my decoder, which is going to do. Okay, now this particular decoder is going to decode which particular block we need to connect using my address bits. So address bits from 6 down to 5, the MSB bit, and after the MSB bit, we are going to use them for decoding the address. And remaining bits, that is from 4 down to 0, that is 5 bits, are used for selecting your memory location. For example, if my 6 down to 5 address of 6 down to 5, if it is equal to 00, then I'm going to select block number 1. Then that means I'm going to select this block number 1. And in this block number 1, which particular location I want to write down, that will be decided by address of 4 down to 0. If it is equal to 5 tick binary 00000, then it means I want to write it down in the first location. Okay, or else if it is equal to some value, I'm going to decide which particular location I wanted to write it. And if I want to have the last block to be selected, then I need to provide the address of 6 down to 5 as 1 1. Then the last block will be selected, and in the last block, into which location you want to write down the data, that will be decided by the remaining number of bits. That is what we are going to do. Is it clear, guys? Is it clear, yes or no? Yes. Okay. So you are going to have how many number of locations? Each block is containing how many number of locations? 32 locations. For representing 32 locations, how many bits do you need? 5 bits. 2 power 5 is 32, right? Okay. And for selecting 4 chips, you need 2 bits. So that's the reason your address is of total 7 bits. In the 7 bits, 5 bits are for 32 number of locations and 2 bits are for selecting your which chip you wanted to select. Okay. Yeah. Now let us start developing of our code and let us see how to develop our Verilog code for this. So let me open Vivado where it is. So let us try to have the Verilog coding for this. I'm going to declare a simple module. Let me zoom in a little bit. Yeah. So I'm going to have a simple module and decoder underscore RAM is my module name. And here inputs are clock, reset, and I'm going to have write enable signal and read enable signal for read operation and also input 6 down to 0 address, which is 7-bit address and input 7 down to 0 W data for write operation for writing my write data and output rich 7 down to 0 R data. Okay. And also for telling my user that whatever the data he wanted to read is a valid data, we are going to have a signal which is known as valid. Okay. So this is my inputs and outputs declarations. Now let me declare one more internal signal which is known as CS. So this CS is used to select which particular chip, which particular block should be selected, and it is of 4-bit. Okay. So why it is of 4-bit? Let me show you. So here I have 4 number of blocks. So I have 1, 2, 3, and 4 number of blocks I'm going to have. Okay. 4 number of memory blocks I'm going to have. And each memory block is going to have an internal signal which is known as CS. Okay. Depending upon the address which was given by the user, decoder is going to, we are going to use a 2 cross 4 decoder logic where it is going to take 2 inputs and it is going to have 4 outputs. This particular logic we are going to consider. And depending upon the address which was given by the user, we are going to decide which particular output should be equal to 1. Okay. Let's say if the user has provided the address as 00, then the output which is corresponding to the first memory block will be made to 1 and this CS will be made to 1 and remaining all will be equal to 0. So we are going to implement this particular logic. Okay. So that's the reason I'm taking one variable which is known as CS. Okay. So according to the address which is given by my by the user, that particular CS pin will be activated. The block, the CS pin corresponding to that particular block will be activated. And I'm going to have, you can also say it as one hot encoding. So I'm going to make only one particular CS to 1. Okay. Yeah. And I'm also going to have something known as 4 down to 0 word underscore address. So what is this word address is nothing but, so in this particular block, these are my words. So total how many words do I have? Total how many number of locations do I have? 32 number of locations. So for representing this 32 words, you're going to have this particular word underscore address which is of 5 bits. Okay. And where are we getting it from? We are getting it from the user only. So user is sending 7-bit address, right? In this 7-bit address, 2-bit is used for decoding your block and remaining 5 bits is used for determining your word location. Okay. That is what we are going to do, which is nothing but my word address. Next. So that is what I'm going to write down the logic over here. So assign my word underscore address, which is equal to address of 4 down to 0. So this particular 5 bits, I'm going to give it to it so that I can able to fetch or whether I can able to decide to which particular location I need to write the data. Now I'm also going to write down my block selection logic. So assign CS of 0, it will be equal to 1 whenever my address of 6 down to 5, the last bits, if it is equal to 2-tick binary 00. If it is equal to 2-tick binary 00, my CS of 0 will be equal to 1. That means this particular pin will be activated and remaining pins will all be equal to 0. If your address, that is first two bits MSB, that is 7th bit and 6th bit, are equal to 00, then this pin will be activated. And the same logic we are going to write it down over here. But instead of address of CS of 0, we are going to take CS of 1, CS of 2, CS of 3. So CS of 1, 2, 3. And here we are going to make this address 10 and 1. If the address is equal to 01, CS of 1 will be made to 1. If the address is 10, CS of 2 will be made to 1. And if address of 6 down to 5 is equal to 11, CS of 3 will be made to 1. Okay, this is what we are going to make. Is it clear, guys? Yes or no up to here? We haven't started with write and read, right? Just we have started with just the block selection. Okay, is it clear? Any doubts or any queries in this? Okay. Now what are we going to do? We need to declare 4 memory blocks. So for that, I'm going to declare 4 memory blocks. 7 down to 0. Mem underscore block. This is, let's say, block number 0, which is going to have the number locations from 0 to 31. Okay. And let me copy this block, and 4 blocks I have read. So this particular second block is also having 32 number of locations. Third block is having 32 number of locations, and fourth block is having 32 number of locations. And here this is block 1, block 2, block 3. So like this, I'm going to declare 4 blocks, 4 memory blocks I'm going to declare. Okay. Now let's write down the main logic over here. So always at pause edge of clock or neck edge of reset. This is nothing but my asynchronous reset logic, which I'm going to write down. And begin. So if my reset is equal to 0, then what I'm going to do is I'm going to initialize all the particular memory blocks to 0. Okay, that particular logic I can write it down over here. Okay, now else if, so begin, I can declare one integer over here, and for I is equal to 0, I less than 31 number of locations, I is equal to I plus 1, mem underscore block of 0 is equal to 0. You can write it. Okay, and mem underscore block of I is equal to 0, and mem underscore block of block 1 of I is equal to 0, and same I will copy paste over here. Okay, within and beginning block you are going to write it down. Okay, now else if reset is removed, then we are going to write down our write logic. So how to write down our write logic? So we need to check for our write enable. If it is equal to 1, then we are going to perform our write logic. Now we need to have the our chip select. Okay, so if our chip select, if it is equal to 4 tick binary 0001. Okay, if it is equal to 4 tick binary 0001, what where I have written over here. Yeah, so if your chip select is equal to this is here, the chip select is nothing but chip select is equal to 4 tick binary 0001. Okay, here the chip select value is 4 tick binary 0010. Okay, and here my chip select value is 4 tick binary 0100. Why? Because you can see over here CS of 0 is 1, that's why here at the LSB position it is 1. Here CS of 1 is 1, that's why here you can see 1. And CS of 2, next is CS of 3 is nothing but CS is equal to 4 tick binary 1000. Okay. So depending upon my address, I have my chip select values. Okay. Yeah. So next, what I'm going to do, I'm going to have my chip select. So according to my chip select, what I'm going to do is I'm going to decide to which particular memory address I'm going to write down. So block underscore address, which is equal to, sorry. So if it is equal to 0001, then it is mem0. That is first block. I'm going to write down my data, W data. And if it is equal to 4-tick binary 0010, then I'm going to write down into my second block, block underscore address W data. Okay, let me copy this and paste it over here. Depending upon my chip select values, I'm going to decide to which particular block I'm going to write down my data. Okay, so this is 0, this is 1. Okay, is it clear, guys? How to perform the write operation? Is it clear? Yes or no? Someone has asked it. How we are going to perform the write operation? Is it clear? Yeah. Now, next, what we are going to do, we are going to end this particular case and end the begin block which we have started. Okay, and that's it. And followed by default statement. Also, we can write it down. Okay. Default is not necessary over here. Yeah. So this is what we are going to do over here. And let me end this begin block which we have started. Okay. And for our begin, if begin, okay. Yes. Now, next comes my read logic. So that was my write logic. Next comes my read logic. So in the read logic, what I'm going to do here, again, I'm going to have my passage of clock or reset if it is applied. Then first I'm going to check for my reset signal, reset underscore n. If it is equal to 0, then what I'm going to do is I'm going to make my R data is equal to 0, 8 tick H 0. Okay. And also I'm going to make my valid is equal to 0. That means there is no valid data which is present if your reset is applied. And else, if you're going to apply your read enable, if your read enable is equal to 1, then we are going to begin this. And depending upon your again chip select, depending upon your chip select, you are going to decide from which particular location or from which particular chip you want to read the data. Okay, that we are going to decide. Okay, let me write it down over here. Our data is equal to mem of uh, word underscore address. Okay, and again the same thing. Let me copy it over here. Okay, and over here this is mem0 mem underscore block 0. Let me copy block 1, and this is block, and this is block 3. So depending upon what uh, particular address they are providing, that particular block will be provided, and from that particular address the data will be read. Okay, here I'm going to give 1, and here I'm going to give 1. One. Okay, and by default let us make our R data to 0. R data is equal to 0. Okay, and followed by end case, end and end. Okay, this is what we have written for our read logic. That's it, and followed by end module. So this is what we are going to write it down. And here our data, I think word underscore addr. Let me check where is word underscore addr declared. Okay, let me change it to word underscore addr. Okay, yes, and okay, it is word underscore addr. Okay. Yeah. And what else we are getting here? Mem underscore block. It is mem underscore block 0. Okay. Let me change the names. Just the name is different. That's it. This is mem underscore block 1, and this is mem underscore block 2, and this is mem underscore block 3. That's it. Okay. Yeah. So this is how I'm going to write it down, and where else we have the error. That's it. So this is the code for our RAM design. For this, we are going to start our verification, and we are going to develop our test bench, and we are going to first of all see the V plan, and we are going to see what are the test cases we are going to have. Yes. Any doubts or any queries in this? Yes. So in the case of write operation, first of all, you're going to have the 7 bits of data. And in this particular 7 bits of, sorry, not the data address, the first 6th and 5th bit are going to be used for selecting your block, and the remaining bits are used to select in which location you wanted to write the data. For example, 6 down to 5 is 00. That means you're going to select block 1, and 4 down to 0 is used for having your word location. Okay. So depending upon that, you're going to provide the write operation. So first of all, you can see over here, depending upon your chip select, if it is equal to 001, which is given by the decoder, then mem underscore block 0 will be selected. This memory location will be this memory will be selected, and in this memory, whatever the address you have provided, that particular address will be used for writing the data. Is it clear? Yes, we can have everything in a single file, but that will be confusing, and it's not a good practice actually to have everything in a single file. Read also the same thing. Haven't you observed over there?